Hello, my name is Jose Hernandez, and today Trent and I will be proving Proposition 26 on the Euclid book, which pretty much just states that we are given two triangles, and we know that the angle let's label this triangle ABC and this triangle XYZ. Oh, C, not Z. And we are given that angle ABC is equal to angle XYZ, these two right here, and angle ACB and angle XZY are equal, and we also know that the side length BC is equal to YZ. And in this first part of the video, I'll be using the angle side angle theorem in order to prove that triangle ABC is equal to triangle XYZ. And in the second part of this video, Trent will be proving it, but using the angle side theorem. All right, so to begin with, we'll be assuming that the side length AB is shorter than the side length XY. And let's say by using proposition 3, we create a point D right here. Therefore, we get an equivalent side length BD to X and Y. So right here, a side length BD is equal to X and Y by proposition 3. And by using postulate 1, we can also create a third line that connects DC by postulate 1, which means you can connect 2 points to each other. And now since these two are the same length right here, we now have side, angle, side. This pretty much means that these two triangles are equivalent by proposition 4, the sine and angle sine theorem. And since those are equal, we are now given that the angle DCB, the angle DCB is also equivalent to XZY. But if you can recall, we are given that angle XZY is also equivalent to angle ACB by common notation 1. We should also get that angle DCB is equivalent to ACB. But by common notion 5, it says that the whole is always greater than the part. Therefore, angle DCB cannot be equal to ACB. Yeah. And our assumption is also incorrect. Thus, angle AB has to be equivalent to angle XY. Now we are given these two triangles. Now that we know that these two side lengths are equal to each other, we can also use, again, proposition 4, the side angle side theorem. We have side angle side, side angle side. And because of this, we know that triangles ABC and XYZ are congruent or equal. And that is what we wanted to prove. All right, so in this next part of the video, Trent will be showing you the same thing, but using the angle side theorem. Thank you.
Hello, my name is Trenton Hicks, and today we're going to be looking at Proposition 26 from Book 1 from Euclid. This is going to be part 2. We actually just heard from Jose, who proved part 1, and it's what we normally know as the angle side angle theorem, where the side that is congruent between the two triangles is the side that is in between the two angles that are congruent between the two triangles. But Euclid goes on, and in the same proposition, he supposes that in a separate scenario, that there's congruence between one of the sides that is subtending one of the congruent angles. So to put that more plainly and remove the jargon, across from this congruent angle right here, there is side BC, and across from this congruent angle, which is also congruent to angle BAC. This angle right here, EDF. Across from this angle, we have this side length right here, this side right here, EF, and we're going to assume that those two sides are congruent. And eventually, what we wish to show is that there is congruence between these two triangles, that is ACB is congruent to triangle DFE. And we're going to try and do this by contradiction. So whenever we prove by contradiction, we're going to want to assume something. And we want to assume that one of the sides, since they're not congruent, we're going to assume that the side length of AC is actually greater than the length of DF. Okay, so basically we're just picking one of these sides to be greater, and we're saying that this side, the length of this side is greater than the length of DF. So from proposition 3 from book 1 from Euclid, if we have two sides that are different lengths to line segments, namely, we can pick a point on one of the on the larger line segment where the distance between this point here, C, and this point up here, which I'm going to call G, is congruent to this side over here. And again, we can do this by proposition 3 from book 1 of Euclid. So now we have a new fact, we're supposing that CG, namely the length of CG, is congruent to FD. Next, one of Euclid's postulates says that you can connect any two lines, any 2 points in space with a line, and that's postulate 1. So we're going to go ahead and say we're going to connect B and G, and just to make this a little bit more pretty, we can use a straight line and connect these 2 points, B and G. So great, we can see that we have a new triangle here with this side length being congruent to here. This angle congruent to this angle, that is angle DFE congruent to angle GCB. And we also have a side length here. This base is still congruent between triangle BGC and triangle EDF. And that sounds familiar because in proposition 4 of book 1, Euclid actually lays out the groundwork for the side angle side theorem that says 2 triangles are congruent if they have a side, an angle, and a side that is congruent between them. Then the 2 triangles overall must be congruent. So we can say that triangle BGC and triangle EDF are congruent. So that's not all we can actually say. We can also say, since these 2 are congruent, that this angle right here, that is angle BGC, is congruent to angle EDF. So I'm going to go ahead and write that down. So from what we've seen so far, angle BGC is congruent to angle EDF. And from our given statements up here, we also know that EDF is congruent to angle BAC. So we're also going to say that all of this is congruent to angle BAC. So namely, we have this BGC over here angle that's congruent to angle BAC. This may seem a little bit fishy to you because these do look like separate angles just from the drawing, and it actually comes out to be 2 separate angles, because back in Proposition 16, Euclid describes a relationship between exterior angles and opposite interior angles, which is exactly the relationship we have going on right here. Namely, that these exterior angles right here, this angle is an exterior to this triangle BGA. This exterior angle is going to be greater than this angle in here, BAG. So let's go ahead and write that down. This is by Proposition 16 in Book 1. So we know that angle BGC has to be greater than angle BAC. And this is an issue because we just showed that BGC right here and BAC were congruent, and in the next step we contradicted ourselves. So what does that mean? It means our original assumption must have been false. So that's this assumption right here. So I'm going to go ahead and clear some of this just so we have more room to think. So what does this mean? Well, since this assumption is false, we have to take the negation of this statement, which is that AC is not greater than DF, so it must be the case that AC is less than or equal to DF. But if AC was less than DF, we could make the exact same argument on the other side. So it must be the case that AC isn't greater than or less than DF. It must be the case, because we could make the exact same argument on the other side, that AC and DF are congruent. So again, that's, switch colors here just so we can get a more idea what's going on. That is this side right here, AC. This side is congruent to DF. So now we have a side that's congruent. We have 2 sides that are congruent. We have an angle between them that is congruent. And we also have another side right here that is congruent. Just for clarity, I'm going to erase this little bit and be very careful not to destroy my triangle. There we go. And we'll get rid of that as well. Again, just for clarity, AC and DF are congruent. So we have this side right here, AC, this side right here, DF. We have an angle between them that is congruent to each other. That's ACB and DFE. And then finally, we have a side between them that is congruent as well. And that must mean that by Proposition 4 of Book 1 of Euclid, that these 2 triangles are congruent by what we refer to as the side angle side theorem. And just to check, that's exactly what we set out to prove. So we can go ahead and make our QE